Hi, this is Rebecca Borchering, and I'll be leading this session on stochastic simulation models. So we can go ahead and get started. Our goals for this session are to understand the motivation for using stochastic models, and then look at two different types of stochastic simulation models. So both discrete time and then event-driven, part 1 and part 2. And then we'll want to be able to relate these models to the differential equation models that you've seen earlier in the week, and then recognize potential benefits and limitations of these different types of models. Just to locate ourselves on the model taxonomy. So today we're starting with discrete time chain binomial type models, Reed-Frost models. But before we jump into the stochastic Reed-Frost, we're going to start with the deterministic version to lead us into the stochastic version. And before we do that, we should probably talk about what deterministic and stochastic mean. So deterministic means that a process proceeds without an element of chance. So if for the starting conditions and parameter values, you'll always get the same outcome every time you run a simulation, for example. On the other hand, with stochastic events or models, these incorporate an element of randomness or chance. So even when you start with the same initial conditions and the same parameter values, you can have different outcomes based on these different runs of your simulation. So why might we want to use a stochastic model? So one of the first things I think about is demographic stochasticity, and this comes out of having discrete individuals. So for each individual, you can have an event happen or not happen. And this could be an event like death, getting infected. Importantly, for small populations, you can think about extinction. So if you have only one individual remaining and it dies, then you have an extinction event. Another reason to use stochastic models is that data is often noisy, even in traditional experimental settings, but particularly in infectious disease systems that we observe out in the world, and also especially for wildlife populations, where you not only don't observe all events, so in particular infection events are really hard to observe, and you may also have small sample sizes where it really you don't have any of the averaging benefits that you get with larger samples. And then one more source of stochasticity that might be important for your investigation is environmental stochasticity. And so these long-term variation in external drivers change the rates, and these could include birth and death rates. So here I have an image of temperature changes for different locations, and we can predict to some extent how things might play out, particularly over short time scales. But if you think about year to year, there are these stochastic events and changes that result in having an element of chance in the processes we're thinking about. So population size is definitely one of the first things I think about when I think about whether or not to use a stochastic model. And here I'm showing so it's an infection. The two types of events that you can have are gaining an infectious individual or having a death. for 3 different population sizes, n, 10, 100, and 1,000. And so for this model, black line is the ordinary differential equation version. And so that's a deterministic model. We often think about using these models for large or infinite population sizes. And then the red pathways are, so there are 10 different paths in each of these panels, and those have so they are able to capture that finite population size with discrete individuals. So you see there are these distinct events of gaining an infectious individual or losing an infectious individual. And this I star is the steady state that corresponds to the equilibrium of the deterministic system. And for this particular study that I referenced down here at the bottom, we were interested in the probability of extinction versus the probability of achieving the value of this steady state. So that's why these panels are shown in this way. But more importantly, the big picture is that for small population sizes, you can really tell that there are differences between the stochastic paths and the deterministic approximation. And so I'll note these ones are in the same, so the scale is different, right? So for 100 individuals starting at 1, so we see the jaggedness of the stochastic simulations, and they look a little bit more like the deterministic solution. And then they look even a little bit more like it for 1,000 individuals. But we, so if you're thinking about a model or a situation where you have a few number of individuals, the deterministic solution or model might not be capturing behavior that you are interested in. And also the extinction events, you are not able to capture those concretely with a deterministic model. So getting into the 2 approaches of stochastic simulation that we'll be thinking about, so discrete time and then event-driven, what do those mean? So discrete time simulations are those which have a fixed amount of time in between steps. So you have a current state and parameter values at a current time t, and then your simulation moves forward a fixed amount of time, delta t. So at each step, you update the state and parameter values, and then you have those updated values at time t plus delta t. So this is different from event-driven simulation, where you have a non-fixed amount of time in between the events. So you again start with a state and parameter values at a time t, but then you generate the time to the next event, we'll call it tau, and the event type. So tau is often drawn from a distribution, a probability distribution. But the important part is that it's not fixed. So it varies from event to event. But again, you update your state and parameter values, and then also the time to t plus tau. So that was just a quick introduction to our stochastic simulation session, and I'll see you shortly for part 1.